So thanks, Andrea,
No, wait,
for...
wait.
Okay.
It's not sharing.
So Andrea did a good job of presenting graphs, which was, I think, originally supposed to be my job. I guess I wanted to maybe take my 3 minutes and use graphs as maybe a communication tool versus sort of a cutting-edge architecture. So this project sort of takes a step back from what Andrea and folks who are working on Illustrious and Simba, these more complicated hydrodynamical simulations, and looks at pure dark matter. So this was supposed to spin, but this is sort of these are largest halos from one of the Kyoto suite simulations. So this is much, much coarser resolution represented here than what Andrea was showing in his hydrodynamical simulations. But the point is that the data product that you might work with from a raw set of survey data is just a catalog of galaxies. And here we're using the Paulman's approximation and just using the dark matter halos underneath, which we obviously wouldn't have. But what we'd like to do is put this structure, encode some physics, some symmetries that we know about the data, like Andrea had mentioned in the questions, and see if this improves the information extraction at the level of the neural network. Another way to phrase this is, how responsive is your neural network to the data representation that you feed it? So you've got these CNN architectures, you've got GNN architectures, which can consume a massive amount of data, squish it down to what we want in the end. We don't know what they're learning. So the idea here behind graphs is that you can split it into a tuple of features. You've got your nodes, you've got your edges, and these can mean something physically if you attribute those attributes to them. So the nodes here will just be the halos and their masses, and maybe not their masses, and the edges will be the relative positions and angles between them, much like what Andrea spoke about. And graph neural networks just take a series of embedders and try to put this into a latent space that we can learn or tune via gradient descent based on some condition. And the condition that we decided to use here is, again, supposed to animate, is the Fisher information. So there's a big body of work on information maximizing neural networks, which uses a metric that cosmologists are familiar with, i.e. the Fisher information, which quantifies the amount of uncertainty we have about the cosmological parameters we're interested in. And we actually use this as our optimization objective. So what you can see behind this likelihood box here is that the whole graph structure and the neural network and the simulator and the halo construction within becomes part of your likelihood. So we're looking at this connection between parameters, data, and summaries. And using these graphs by increasing the connectivity, the descriptivity of the attributes on the nodes and the edges, we hope to extract more information, or in this case, because it's a very limited example, show that the information extraction is made more efficient. So an example of that is if you throw a bunch of point particles, x, y, z coordinates in as a point cloud. This is what we call a non-invariant graph. But if you encode some relative positions, the universe doesn't care if you hold it upside down. At least the cosmological parameters you generated this graph with doesn't care about that orientation. And you can see that this information, the neural networks and the optimization scheme we put together can figure this out regardless, but in the top row, we encode a bunch of symmetries. And you can see these training curves are a lot more efficient. The network is much happier to play with the data. And then if you just throw a bunch of point clouds, you see a bit sort of messier and longer training curves, but we generally get to the same amount of information extraction. But again, encoding symmetry, this is just an exercise in communicating to the network and your data construction so that symmetries work and physics works. And what I'd like to do is just take the last couple of minutes and take a look at this result. So in this formalism, we're also able to compare to existing summary statistics. And a byproduct of the optimization scheme we use is that we have a Fisher matrix that we can interrogate directly without having to do fancy SPI. So if you take the halo catalogues that we generated our graphs from, and you compute the 2-point information, and then you compute the Fisher constraints from that observable, you end up with this dashed ellipse in omega m and sigma. These are the parameters we're interested in this study. And then if you take a look at sort of an approximation to the halo mass function, again, there's an n-body simulation, so we don't have this real example, real-life halo mass function under the hood. But you can take a press sector mass function and guesstimate what the constraints would look like. So those are the dashed lines you see going perpendicular almost to the 2-point information constraint. And the graph sort of combines both of these statistics in one. You've got the halo mass, which you can probe by making a cut and changing the cardinality of the structure, or by explicitly labeling the mass of the halos. And obviously you have the clustering information because all of the nodes are interconnected. So the graph becomes a combined statistic. Again, we're not reinventing the wheel. We had an idea that these things existed before we constructed our massive n-body simulations. But it's a nice way to show what your machine is learning. And if you can't reconstruct existing statistics, then you should probably take a step back. And but the added thing that we can do in this framework is construct a catalog using realistic noise. So we can make a mass cut, and we can train to produce these informative combined summary statistics out of the end of the GNN by re-simulating our halo catalog cuts over noisy masses or whatever your observable is many, many times. I mean, this is sort of the advantage to simulation-based approaches. And obviously, if you increase the uncertainty in your masses, you will increase the uncertainty in your results. And this is just sort of a saliency, sort of a sanity check that we did at the end. So what's also cool about this limited analysis, you can run the whole thing in your browser. So I've got some code if you guys want to chat to me afterward. Obviously, just like Andrea mentioned, we've got a long way to go before we can adapt this explicit architecture to data. But again, this was a response to the frequently asked question, some of my other projects, of what is your neural network actually learning? So thanks so much for your attention. I think I went over time. So.
Thanks, Lucas. So we already passed the hour. I guess we'll stop there. Do we? Yeah? Short questions? Okay, so we'll allow for some short questions about the flash talks we had during this session. Is there any question for our speakers in the audience? Yes, there is one there.
Thank you. It's a question for the last speaker. No worries. Did you try to include redshift space distortions to your distribution? Because I guess that the noise that you have been adding was kind of a homogeneous noise. So I guess that adding redshift space distortion will distort, in fact, the distribution and the links, and most likely increase or modify your ellipses.
So no. Again, there's sort of a limited example. So we're working with the perfect Kyoto cubes, which obviously you'd be working on a light cone in reality. But what's, again, another plug for this sort of graph neural network architecture scheme is that you can sort of make your coordinates whatever you'd like them to be, right? So really, my evangelical statement is that every data structure that you can come up with is actually a graph. It's just constrained to some manifold. So if your redshift space distortions, or let's say redshift could be one of your 3 coordinates, for example, spatial coordinates. And if you confine yourself to a sphere, you could reduce to 2, but those could be angular coordinates, right? Just the same.
Yeah. Thank you. Do we have any questions from New York for our speakers?
Any questions for Flash Talks? No, I don't think so. Thanks.
Any other questions in the room, or is there any question on Slack? There was a lot? Okay. I remind people, yes, and I encourage people to use Slack to ask as many questions as you would like. If there is a last one, we can take it, otherwise we'll go to the coffee break. Okay, so coffee break for everyone. Thanks to all our speakers.